Hello everyone, and thanks for watching Edupedia World Videos. In this video, we'll be learning about the dynamics of circular motion. We've seen two aspects of motion till now, kinematics and dynamics. Kinematics is the study of motion of a body when it's not really concerned with the cause of motion. We study where the body is, how much is the acceleration, where it will be at a particular time and so on, but we are not really concerned with what are the particular events happening that cause the body to move in this particular way. Dynamics also involves the study of causes of motion, which we've learned in Newton's laws of motion are called forces. So let's get into it. We've seen kinematics of circular motion earlier, and now we'll expand our knowledge to dynamics of circular motion. So first let's take a little bit of a recap of kinematics of circular motion. So let's say I have an object moving in a circle of radius r with the speed v. Now at any instant the direction of this velocity is going to be tangential, right? So we've seen that if the speed is constant, then there is only one acceleration, which is towards the radius, towards the center. But if the speed is changing, there is also a tangential acceleration. So there are two aspects of acceleration, one which we'll call AR, which is the radial acceleration, and we derived its value earlier, and it is equal to v squared by r. It's equal to v squared by r, and its direction is towards the center. So this will be AR. The magnitude is v square by r, the direction is towards the center. Now we see as the object moves along the circle, the direction of AR changes. For example, if the object moves and after some time it reaches this point, this is supposed to be tangential, I apologize. And I'm sorry. So let's say initially its speed was v1, direction was this. Finally, later its speed becomes v2, and this is the direction. So now the acceleration also has its direction change along with the magnitude. The magnitude of radial acceleration now is v2 square by r, but the direction is also different. So the direction of radial acceleration changes continuously. The second type of acceleration, which only exists if v is changing with time, is tangential acceleration, and we denote it by at. And since acceleration is a vector, we need the magnitude and the direction. The magnitude is dv by dt, that is the rate of change of speed, and the direction is tangential. That is the same as the direction of instantaneous speed. So this is AR, and in this direction we'll have AT. Now obviously the radial and tangential directions are perpendicular to each other, so these are two independent components of the acceleration vector. So we can find the magnitude of the acceleration vector. That will be, we'll use the triangle rule of addition. So it will give me AR square plus AT square plus 2 AR AT cos theta, but cos theta is 0 since theta is 90 degrees. Or you can directly use Pythagoras theorem as well. So the magnitude of acceleration will be root of v squared by r whole squared plus dv by dt whole square. And you could also find the angle with anyone. For example, the angle with the radial direction will be theta is tan inverse of dv by dt by v squared by r. So we've seen all this previously, right? We've derived the formulas, and it's better to know the derivation than to just know the formulas, as you'll be able to solve even more deeper questions then. Now we'll do just a simple addition. We'll use Newton's second and first laws to be able to find out the forces which cause these acceleration. So if there is a radial acceleration of magnitude v square by r directed towards the center, that automatically implies that there must be a radial force. But in the terminology of circular motion, we generally call it centripetal force. Radial or centripetal force. Right? And its magnitude is mass times the acceleration. So it will be mv squared by r. And the direction will obviously be towards the center. Similarly, if the speed of the particle is changing, velocity has to change, remember, no matter what. But if the speed is changing, then there will be a tangential acceleration which will be caused due to a tangential force. And we label it as Ft. Its magnitude is m dv by dt and its direction is tangential. Right? So let's try to apply these in a few problems. Now, one thing we need to remember is when we solved problems of Newton's laws of motion, after making the free body diagram, we decided to resolve and write equations in any two perpendicular directions. And I told you sometimes it may be obvious which directions to choose, sometimes it may not be. But no matter which directions you choose, you'll get the same answer. The only question is the simplicity of the equations. In some cases, for example, horizontal and vertical directions, if they are taken as x and y, the problems becomes much simpler. In questions involving circular motion, it is generally most convenient to take the two perpendicular directions as the radial and the tangential direction. So you figure out in what plane and in which sense the circular motion is occurring, and then you resolve the free body diagram. You make the free body diagram, and you resolve forces into two perpendicular directions, radial and tangential. So let's take the simplest case of circular motion, a simple pendulum. So here I have a bob of mass m which is attached to a rope. Let the length of the rope be r, and I just leave it and it is moving under gravity, and at any other instant it might just make a random angle. Let's try to measure it all from the center. Right. So I label this as theta, and I label this full angle as theta naught. Theta naught is called the angular amplitude of the motion. If you move a simple pendulum, it moves to a certain angle where its speed becomes 0, and then it moves back. It moves to and fro between these positions. So the maximum angle between the rope and the central position, theta naught, is called the maximum angular displacement. At any point, the displacement is measured in theta. We saw this earlier in kinematics. In motion in a straight line, we measure displacement by position, by the meters or the kilometers. In circular motion, we measure position by the angle. Right? So let's take this particular instant. We know that at these two instants, at the end points, speed will be 0. Right, that is the definition of maximum height, right? Speed is 0. So when you have the maximum displacement, there will be no more displacement, so speed will be 0. And obviously angular speed will also be 0, because v is omega r. Let's consider this instant where it is at a random point, not at an extreme point and not at the central position. And let's say it's moving tangentially with a speed v. Right, so we need to draw the free body diagram. Now this angle is drawn quite small, but I'm going to enlarge it in the free body diagram to make the figure clearer. Right, so this is my object. Obviously, since it is happening on Earth, there will be an mg acting downwards, and there is a tension acting at an angle theta. Right, so there is no other force acting, there is a tension and there is the force due to gravity. So we've drawn the free body diagram. Now let's try to resolve it into two directions. We could try to take the horizontal and vertical directions, but like I told you, in circular motion it is often easiest to choose the radial and tangential directions as perpendicular directions. So this direction, the direction of t, this is my radial direction, and this direction perpendicular to it, it is my tangential direction, in which direction the particle is moving with the speed v. Right, so we'll resolve into these two perpendicular directions. Right, so what is the acceleration? Let's take two accelerations, let it be AR and AT. Right, so first let's write down the equation for the radial direction. If this is theta, due to vertically opposite angles, this is also theta. So the equation in the radial direction will be T minus mg cos theta is equal to m AR. And what is AR? AR is v square by r. Right? And in the direction perpendicular to it, that is the tangential direction, the component of mg will be 0, the component of t will be t sine theta. Sorry, the component of t will be 0, I apologize. The component of t will be 0 since this angle is 90 degree, and the component of mg will be mg sine theta. So we'll have mg sine theta is equal to AT. So if we had two unknowns, the tangential acceleration and the tension, then we found out both of them. The tension is equal to mg cos theta plus mv squared by r, and the tangential acceleration is g sine theta. Sorry, this should be mat. My bad. So the tangential acceleration should be g sine theta. Right? Now, just to make it easy for you, just to make you realize that we can actually resolve the equations into any two directions, I'm going to try to resolve the equations into the horizontal and vertical direction. And I'm going to try to show you that the answer will be the same, though maybe the equations might be a little bit more complicated. So let's down the answer to these equations directly. We found out t to be mg cos theta plus mv squared by r, and we found out at to be g sine theta. So now let's try to resolve it into the horizontal and vertical directions. Right, so this is my tangential acceleration at, this is my radial acceleration, and this is theta. So now I will have to take the components of the acceleration as well. So let's take the horizontal direction. In the horizontal direction, mg has no component, t has a component, t sine theta. So my first equation will be t sine theta is equal to mass times the acceleration in the horizontal direction. What is the acceleration in the horizontal direction? This is theta, so this is also theta. So the acceleration in the horizontal direction is actually AR sine theta plus AT cos theta, right? They both have a component in the horizontal direction. So AR will be v squared by r sine theta plus AT cos theta. So this is my first equation. The second equation in the vertical direction, so I can take either the upward or the downward direction to be positive. The only difference will be both sides of the equation will be multiplied by minus. I'll take the upward to be positive. So my equation becomes t cos theta minus mg is equal to, the acceleration in the vertical direction is AR cos theta, mass times, that is v squared by r cos theta, minus, because this is in the downward direction now, AT sine theta. So now these are my two equations. I leave it to you to try to solve these equations. Everything is known to us except AT and t, right? So using these two equations, try to find out AT and t, and you'll be able to see that we'll get the same answer, though we see that the equations are more complicated than this. You can easily see two of these equations are simple and two of the equations are slightly more complicated. Right. Let's move on to another type of pendulum, now a conical pendulum. Now we'll reach a position where sometimes students get a little bit of confusion, because we'll see equations that look similar to these equations but slightly different, right? And you'll get confused if you try to correspond equations to questions and try to remember it. If you try to remember the fundamental principles, then you'll see that the questions themselves have slight differences, and by using the principles you'll get the slightly different equations. You'll see what I mean in a little bit, right? So the next case we'll see is a conical pendulum. So let's call this L. Why not R? That will be clear in a moment. This is a conical pendulum. In a conical pendulum, the difference is that the motion is not occurring in the plane of the screen. You're watching this video on a monitor, and if you saw the previous case of simple pendulum, the motion was occurring in the plane of the monitor. In this case, the motion is occurring in the plane perpendicular to the monitor. It is occurring in a horizontal plane like this. You can picture it as an inverted cone, right? So in this case, if I just, the difference comes from this. I'll tilt a rope to the side, and if I then push it downwards, it will move in this direction. But if I push it inside or outside the plane, it will start moving in a cone, right? You can see that. So we'll try to analyze this. Now, if you try to remember the equations, you'll get confused. Remember the principles, and the difference in this case from the previous case is the motion of the circular motion is occurring in a completely different plane. So hence the equations are bound to be different, right? So think about it carefully. In this case, this is the plane of motion. This R is the radius, right? Let's say this angle is theta. This L is the length of the rope. Then R equals L sine theta. So we see the first difference already. In the previous case, the radius of the circular motion was the length of the rope. In this case, it's not the length of the rope. In the previous case, this was the center of circular motion. Now this is the center of circular motion, right? So in this case, again, we'll try to resolve it into perpendicular directions. We'll take this horizontal direction, which is the radial direction. The tangential direction is not really of significance to us in this case, if we are given that it's happening with constant speed, which I'm giving it to you, and we'll use the vertical direction, right? So let's draw the free body diagram of the object. As usual, mg, and in this case T. We see that the forces in this case are exactly the same as in the previous case. However, the accelerations are very different. This is the free body diagram for this point A, right? So in this case, the acceleration towards the right is v squared by r, the radial acceleration. And given that it's moving with a constant speed, the tangential acceleration, that is the acceleration perpendicular to the plane of your screen, is 0. And in the vertical direction, there is no motion, since the motion is occurring in the horizontal plane. So the acceleration in the vertical direction is 0 as well. Writing the equation for the vertical direction, I get t cos theta minus mg equals 0. And horizontal direction gives me t sin theta equals mv squared by r. Right? So we've just added one small aspect into our previous knowledge of Newton's laws of motion. That is, we take the directions to be the radial and the tangential directions, and then we apply Newton's laws of motion as usual after drawing the free body diagram. Right? Now, we saw what pseudo force meant. Let's see the analog of that in circular motion. Right? So pseudo force, we derived it to be equal to the pseudo force that was equal to minus the mass of the object, the acceleration of the frame. This is very important. The mass of the object, the acceleration of the frame. Not the mass of the frame, not the acceleration of the object. This is the way to do it, right? So if you're working from a non-inertial frame which has a particular acceleration, then all you need to do is apply the pseudo force, which remember is not a real force, and somehow the machinery of Newton's laws of motion will work in such a way that will give you the correct answer. Or you could just choose an inertial frame and do it that way as well. So if there is a frame which itself is rotating at an angular speed omega, let's say you're standing inside a lift and the lift is moving about its center with an angular speed omega, and you are inside the lift. So you are also moving at an angular speed omega, right? Now if you try to solve a question of Newton's laws of motion, let's say you throw a projectile or there's somebody applying a force to an object, it will give you the wrong answer because currently you are in a non-inertial frame. You are in a frame which, even if it is moving with a constant speed omega, there is a radial acceleration equal to mv squared by r, which will be equal to obviously m omega squared r, since v equals omega r. We saw this in kinematics, right? Remember this. So their acceleration will be v square by r or omega square r towards the center. So if I am standing in this frame with an acceleration omega square r towards a certain point, then to be able to apply Newton's laws of motion correctly, I need to apply a pseudo force. So the pseudo force will be minus m omega squared r. Minus because it should be in the opposite direction. So this will be in the radially outward direction, not the radially inward direction. And the name for pseudo force when it is applied to circularly moving frames is called centrifugal force. Right, so we saw two different types of forces, centripetal and centrifugal force. Centripetal force is the very real force which causes an object to move in a circle. Centrifugal force is a pseudo force, it is not a real force. It is a force we apply when we are solving a question in a non-inertial rotating frame of reference, but we still would like to use Newton's laws of motion. Right, so remember the difference between the two. Right, this completes dynamics of circular motion. In the next video, we'll start a new unit called work. Mechanics for motion for us has been completed. Thank you.